what I'd like to do today is talk a little bit about operating systems in general, why you may want to know about them. Most of you probably already have an answer to this, otherwise you wouldn't be here. But just let me talk a little bit about it. Then I want to talk a little bit, very briefly, about the structure of the class. And then I'm going to get going basically and talk a little bit about operating system abstractions. You'll see through the semester that a large part of this class is about sort of designing good abstractions. And so we're going to look at a couple examples. One to sort of give you an idea about what are some of the issues and what does a good example look like. And we're going to do that by sort of case study by looking at the Unix OS abstractions. Functions in as a second row, namely that you're going to be implementing basically an operating system that supports sort of the core Unix abstraction. So it's nice to know what you actually have to implement. Okay. If there are any questions or general questions, feel free to ask them or interrupt me at any point in time. Actually, I'm delighted to have questions and any discussion that you might want to have. Okay. So I'll get a little bit into details about exactly the logistics in the class, but if you have burning questions right now, then feel free to ask them. All right, so let's get going then. All right, so the main goal of this class is to make sure that at the end of it, you actually understand what an operating system does, how it's built up, how it's engineered, what the issues are, and feel very comfortable with the material. And we should be able to, at the end of this class, to sort of look at any real operating system like Linux or Windows, if you get the opportunity to look at the Windows source code, and understand actually what's happening. Might have a little bit of studying, but to do it in principle, that should be possible. And then I guess there's an underlying second theme why you may want to take this class is that it applies a lot of the 6033 concepts that you've seen. Who's taken actually 6033? Many of them you should have. Okay, so for everybody who's taking 6033, you get sort of an opportunity to apply the principles and ideas in 6033 for real by building a real system yourself. Right? In the end, a lot of this class is about building a system. And so all the lessons you've learned about system building are going to be applicable here. Now, why do you want to study an operating system? It's very likely that very few of you actually will build ever a real operating system. You come out of MIT, you can find some job, and it's very likely actually that you will get seriously involved in designing or building an operating system. But there are multiple reasons why to do it. One, you might actually end up doing it, so you need to know it. And particularly, the operating systems are not a done deal. There's a lot of actually open remaining research questions, and so as the world evolves, the technology evolves, and the operating system are evolving, and so it requires some set of people that are actually able to actually write new operating systems and extend them. The other reason actually you really may want to, just curiosity, you may want to know what actually is happening on your computer, so what's happening under the hood. You're all running computers, you're using them, and basically the operating system is a piece of software that turns basically a bunch of hardware into something useful. And it would be interesting to maybe to know actually how that actually happens. The other reason that you actually might care about it, or you need to know what actually happens under the hood, is that if you run any piece of software on it and you care about performance, most applications use the operating system in some way. And if you want to understand why the application performs is the way it is, it's often the case that the operating system is involved in that question and sort of puzzling out why the application is behaving the way it is requires to actually have a detailed understanding of the operating system. So even though you don't do anything inside the operating system, just using the operating system, particularly if you care about performance, you might actually need to investigate, the insights. And that, performance is one reason, sort of curiosity is one reason, performance is a second reason. And the third reason is security. And we're going to not talk much about security in this class. In fact, there's another class, 6857, which is actually right before this class that talks a lot about computer system security. But often the operating system plays an important role in that. Because with security, there only has to be one hole in the system, correct? And you get in, and so you got to make sure that you understand all possible ways of getting in, and that requires often a detailed understanding exactly what the software is doing, how it manipulates the hardware, and you're going to learn all about that in this class. And so if you care really a lot about security, you need to know actually how an operating system internally uses the protection mechanisms of the hardware to provide some degree of protection. But we're not going to talk much about security. In fact, mostly we're going to ignore it, partly because most all operating systems don't really have a great plan for it anyway. So it's not like we have a great example that we can study and say, oh, this is the way to do it. And it's a complex topic in itself. Okay? So that's the reason that you may want to care. So why actually have an operating system? Right? You can imagine, so what is the alternative? Let's say if you didn't have an operating system, what would you do? Right, well, alternative would be to run the application just right on the hardware. Right? Get the box with the processor, the memory, the PC, and the screen, and just run your application on it. Like write the assembly. And clearly, we don't do that. But that's sort of a good extreme point to have in your head, because it tells you like a little bit what actually the operating system does for you, right? And so, what are the things that an operating system does for you? Well, it hides a lot of the hardware details. From application programmers, right? When I don't have to worry about, how do I write a character to the console, or how do I read a disk block from the disk? This operating system does it for you. You don't have to worry about that stuff at all. And in fact, a good operating set of operating system instructions allow you to have the same program run on different hardware platforms, and it just works. Right? And you don't have to worry about it at all. So portability is another major reason. Or you upgrade your PC to have more memory. You don't actually have to rewrite your software to actually handle it, because the operating system does it for you. The other reason to do it is that the OS provides a whole bunch of sort of useful common abstractions. So there's a lot of software you don't have to write. You don't have to provide a file system. So you can at least rely on the file system there. You don't have to worry about it. And as an application programmer, you can just assume that it exists. So you don't have to write that code, and it makes your application simpler. The final reason is that you may actually want to run more than one application on your hardware. So remember, extreme was you just write the application, you run your application straight into hardware. What actually if you want to run two applications in the hardware? You got to have a plan for multiplexing the hardware between the different applications, and basically an operating system does that for you, and you don't even have to worry about it. Right? And if you write an application on your computer, you sort of less, as an application writer, you assume more or less that that application has complete control of the whole computer. You can just use as much memory as it likes. You don't really worry about how that multiplexing is happening. Right? It tells you that the operating system has been extremely successful, right, in some sense, because you don't worry about actually how the multiplexing actually happens. So these are things that an operating system does for you, and in fact most of these things you're going to see as you're going to be building your own operating system in your labs. So how does an operating system sort of look like? There first has to be different views on what it could be. There's like the minimal view. View where an operating system is basically you have some hardware, you have a library, you have your application. And the library doesn't means nothing else than hiding the hardware details. And you can think about a lot of real-time systems or real-time operating systems almost in that sense. They don't really do much other than sort of abstracting some hardware details from you, because typically when you're building a real dedicated hard real-time system, you're actually running one application on the system, and you need to have complete control over the scheduling and when events happen. So in the real-time systems, you often see that this is a very minimalistic view of actually what the operating system is, and in fact most real-time application builders, they don't really want an operating system at all, because it takes away control. The more sort of the big view is, well, you got a bunch of hardware, and the OS abstracts that away into an abstract virtual machine, an abstract machine. And it might be a virtual machine, it might not be a virtual machine, but the idea is basically the application programmer does actually not see any of the hardware details at all. It doesn't even know how much memory there in the machine is, how many processors there are, how you write to the disk, how you print something in character on it. It provides high-level abstractions that we're sort of all used to, like file systems, Windows, et cetera, et cetera. Right? And these. And there's a big difference between these two extremes, correct? Because a library on the real-time operating system, whatever, a couple of thousand lines of code, maybe 10,000, while these guys, are tend to be big, correct? Like how many lines of code is there in the Linux kernel? Just to make sure that these pictures are quite different. Any guesses? Or Windows or any sort of like, or Mac?
Some number of millions.
Yeah, single millions, tens of millions, hundreds of millions, billions. Any guess? Could you write it in a single semester? All right, so 50 million. How many people go for 50 million? We have more than 50 million, let me ask. Nobody goes for more than 50 million? One person. Everybody less than 50 million? That's disappointing. Yeah, I think 50 million, more than 50 million is, I think Windows stands above 50 million lines of code. So you're not going to be able to write it in a single semester. And you might just wonder, okay, what 50 million lines of code, what do they do? Well, we're going to talk a lot about, we're going to basically spend the semester, not exactly talking about what every line of code does, but at least going for many major subsystems, and hopefully at the end of the semester you understand, wow, actually, there's some stuff going on there. This is not, not somebody just basically typing the same line in over and over and over, or having bad abstractions or whatever, failing 670 something. There's real code there. Okay. So, but it is important to keep this perspective in. You can have a very small little operating system that does nothing, and you can have a big operating system that does a ton of stuff for you. Part of the size is big is because of device drivers, right? Like many hardware platforms have many different devices. For every device, you need some piece of operating system code that manages the device. So if you have many devices, multiply that, by some number of lines of code per device, and that goes up. And I think roughly, a good number to have in your head is like maybe half-half. Like half is in the device drivers, the other half is actually the core operating system. All right. And that's ballpark numbers, I'm just saying it's not a factor of 100. Okay? So.
You want an actual number?
Yes, I can give you an actual number. Super, always good. What is it?
For the C and H files, 12 million.
For Linux.
For Linux, yeah.
Yeah, but that excludes a whole bunch of stuff.
No, it's all true.
Well, 12 million you're not going to write anyway in a single semester either. Okay, so what are sort of common examples of OS services? What do you expect an OS to do for you? What are common OS abstractions? Scheduling. Yeah. Let's write some of this stuff down. Scheduling is scheduling of what? Sorry? Processes, yeah. Any other things that an OS does for you? I mean, what do all these 12 million lines or 50 million lines of code with
Memory management?
memory management? What does that mean?
Determining what gets put in the RAM or not. Caching. Well, not caching.
Yeah. All right. It's a little bit of an unfair question to ask because I haven't told you what memory management is, but yeah. But basically, the processor or the PC has some fixed amount of memory, and it needs to be divided up between multiple applications, for example. And so there's got to be a plan for how to do that. And we got to look at that. And it turned out to be interesting issues there. Furthermore, what we probably want to do is actually keep the applications out of each other's hair, right? So that when one application has a programming error, happens to write some strange value in some strange memory allocation, it shouldn't affect any other application, right? And so we got to have a plan for that. Any other?
File system?
Yeah, file system. Be nice to store the files, correct? And not have to worry about like individual disk blocks for 512 bytes. Yeah, in the back. Yeah, boots. Yeah, very important. When you press on and off on your PC, something has to happen. Right? Some software has to get loaded. Your operating system has to come to life, and the operating system does that part for you. Basically, a piece of hardware without an operating system is completely useless. Right? So, anything else?
The networking stack?
Yeah, networking. It'd be nice to connect to the internet. You can't log into your Facebook account, right? Yep.
User I/O.
Yeah, I/O. That's good. And even that is a broad topic in itself, right? There's printing things on a console, having windows, mouses, clicking on things, and the operating system basically provides all the infrastructure for that. Right? Anything else? Any other abstractions you might imagine that an operating systems provide? Yeah. Yeah, clock time is actually a big one. We'll talk a little bit about it, but somebody has to keep the time. If you time date, or you want to know how many seconds it passed, the operating system tells you. Yeah.
Communication between processes.
Yeah, correct. Even though we want to isolate processes from each other, it would be very nice if they could communicate with each other. We would like to be the case that some process, when it prints something on Windows, it can communicate with the Windows server to actually get it done. And so we want isolation, but we also want sharing. And so some facilities for sharing between processes is necessary. Sometimes called IPC, inter-process communication. Anything else? It doesn't add up to 12 million lines of code, right?
Miscellaneous things like seeds for randomness.
Yeah, generating random numbers is typically also done by, we won't spend any time on that, but it is important.
User interfaces?
User interfaces, yeah. I think the whole notion of users, correct? Typical operating system allows you to have multiple user accounts, user IDs, and all that stuff, access control. Some files can be shared with some people, not with others, all that stuff. And again, a topic we're not going to spend much time on, but most operating systems provide this. All right. So you got sort of a general idea, about what actually an operating system is supposed to be doing. Now, so the real question, these are sort of our wish list of things that an operating system should be at least do. And so the real question in many ways is how to do that. How to provide these abstractions, how to provide the services. What are the APIs? What's a good API? What's a bad API? And we'll see throughout the semester that a lot of the choice of API is sort of a crucial decision. And you can get it right, and then you have a wonderful, elegant operating system. You get it wrong, and you have a bulky, terrible design. And so we're going to see a little bit of that today, but you're going to see a lot of that as the semester goes on. And you might wonder, why is it hard? Why is interface design for an operating system hard? And we'll see that there's often competing demands, and that make it tricky. So it's worthwhile pointing that out on what is sort of unique or makes it even harder than an operating system. Right? When most of you are taking, a software engineering class, and you might just think, oh, it's just like any other abstraction. And so I've learned that in my software engineering class that this should be straightforward. And that, to some degree, that's true because everything that you learn applies. But there's sort of a couple things that sort of make the tension for doing a good design sort of more challenging. And one reason it's more challenging is, like, on one hand, you want the operating system to extract the hardware for you so that you can move your application from one platform to the other. You don't have to worry about the hardware details. So you want abstraction or hardware abstraction. On the other hand, you want performance. It wouldn't mean great operating system, correct, if you run your application and basically, whatever, 90% of the cycles from your CPU are actually going to the operating system and the remaining 10% are going to your application, right? And so you gotta, there's a real tension to, make sure that, you're not wasting cycles on stuff that actually is not important to the application. Another challenge again, is sort of very important in operating systems. And on one hand, you want it, sort of be very powerful, because you'd like to have as many servers as possible, so that application writers basically don't have to do anything other than writing their particular piece of the application, and then they're done. And so you'd like to have a powerful, general, many features design. Yet on the other hand, for correctness, right, and keeping things reasonably small, you want minimal mechanism, or small mechanism, a few mechanisms. Clearly, this is a very moving target. What exactly how to achieve that goal. And if you have 50 million lines of code, it may be hard to argue about. We'll see actually that in those cases, in general, it's true that sort of the underlying principles or the underlying abstractions are actually not that many, but they can be combined in interesting ways that give you a lot of flexibility. There are often interactions, or sometimes unintended interactions. We'll see examples today. The way you structure your input-output, has some relationship when you create a new process. What happens with the parent process? The parent creates a new process, the child process. The I/O from the parent needs to get somewhere to the child, or there needs to be some plan. So there's interactions between sort of different pieces of the system, different abstractions that actually you can do badly, or you can do very, very cleverly and do it well. But that's one level. Another level might be there's interactions between CPU scheduling and, say, memory management. You want maybe want to have some processes that have high priority so that they get priority over other processes. But the memory allocator might be unaware of this, and it needs to know in some ways that maybe it should give more memory to the high priority processes. And of course, that makes the design certainly complex, because now your memory abstractions need to know about your process abstractions, and before you know it, you got them all entangled up each other, right? And so doing clean design is actually not that easy. Another reason why this is a sort of difficult area is they're just open problems. It's not the case that at the end of this class I can tell you, well, everything about operating systems that you need to know. You will never need to know more. There are problems that we, as the sort of operating system community, doesn't really know how to solve. And operating systems actually develop at an amazing pace. much more capacity than you might think. I was looking at some statistics, for example, for the Linux kernel a little while ago, and I look at the number of changes, code changes per release, and there's a release every 3 months. And any guess like how much changes in per release in the Linux kernel? Like in terms of fraction, like 1%, 10%, 100%, given that's 12 million lines of code. Any?
5%?
Yeah, sort of dead on, sort of somewhere between the 5 and 10%, depending on like exactly the release. So that means that in a 2-year time, sort of roughly the whole operating system has been rewritten. And so there's a tremendous amount of change, right? So it's not a stagnant thing you write once and then you never change it. And there are many reasons why they're changing. Because of new demands, new features necessary, the new hardware platforms, you want to run on many, many cores, use the cores efficiently, et cetera, sort of better security, et cetera. And these are actually things, basically people don't really understand exactly what the exact right solution is. Right. And we'll read some, so this class is structured in like one half of the class is basically, sort of old boring operating system stuff to make sure that you catch up to like what everybody should know. And then the second half of the class is like reading research papers that sort of get you up to speed to like, issues that, currently are important. Okay. Okay, so let me talk a little bit then about the class structure. Start doing that. And then we'll return back to OS abstractions and give you some examples and point out like what some of the good features are.